Yes. What about the attending another speaker? It's okay?
I think he will be there with ma'am. He's the second slot.
I think
Okay.
speaker and the co-speaker, they're together.
Together, I think.
Yes, madam, I think your co-speaker is with you, right?
Yes.
Okay, thanks.
So right now, 6:05:44. You can join, no problem.
Okay. So, Chairman, may I request you to start with your welcome address?
Thank you, Mr. Ram Chakraborty ji, Joint General Secretary. First, let me welcome you all in this very good evening. Dr. Hemanto Thakre, President of Institute of Engineers, Engineer Sandeep Kumar Dev, Vice President, Dr. G. Ranganathan, Chairman, CARTE, Professor Dr. G.S. Mundada, Chairman, Electronics and Telecom Division Board, Engineer Chanchal Chakraborty, Convener of the Division, Dr. Raju Bashak, Honorary Secretary, and Engineer Ramchandra Chakraborty, Joint Honorary Secretary of West Bengal State Center, IAI. Panelist speakers, Mr. Sanjay Kumar Chaudhary and Ms. Munmun Chakraborty, both Joint Directors, CDAC, Kolkata. Past and present council members of the institutions and distinguished corporate members, ladies and gentlemen. It is indeed my great pleasure and honor to be speaking here today in this webinar on quantum computing, organized by the Electronics and Telecommunication Division of West Bengal State Center, IEI. Being the chairman of the State Center, IEI, it is my privilege to address the gathering of eminent engineers and technologists. On this occasion, let me extend a warm welcome to you all, and especially our panel speakers, corporate members, distinguished guests, the staff of IEI, and my beloved students and other dignitaries. The theme of today's webinar is quantum computing, which is basically a subject of computer engineering, though our ET division has come forward to host this program. The worldwide pandemic situation we have since a couple of years forces us to enter into the digital life, where quantum computing is a rapidly emerging technology that harnesses the laws of quantum mechanics to solve problems too complex for classical computers. The technology based on this principle of quantum theory, which explains the behavior of energy in material on the atomic and subatomic level. It is about 40 years since physicist Richard Feynman pointed out that quantum systems should be able to carry out an entirely new form of computation that outperform even the most powerful conventional computers, because they have properties that just don't exist in the classical world. Quantum entities such as atoms, photons, electrons, and the like have access to a different set of routines of information processing if used to make quantum bits or qubits a potentially much more powerful set. Part of that is down to quantum superposition, which means a qubit can be used to represent a complex combination of the 0 and 1 binary states used in normal computing. That doesn't mean that it is 0 and 1 at the same time. A better way to put it is that might turn out to be 0 or 1. Quantum algorithm used a process called interference to skew these undefined properties and bias the interactions of multiple qubits in a way that increases the likelihood that they will arrive at a final state that contains a solution to the problem they are trying to solve. 5 developers of quantum systems have announced plans to have fault-tolerant quantum computing hardware by 2030, and many industry observe anticipate that we will see a clear quantum advantage for a number of applications by then. The US leads the world in quantum computing, where China is the follower. At the beginning of 2019, IBM unveiled its first commercial quantum computer, fast forward to January 2020, and the company claimed that at CES 2020, that they are now in the decade of quantum computing in 2019. Google was first to achieve so-called quantum supremacy, or the operation of a quantum computer that is able to solve specific problems faster than a classical computer. Google announced that by this Sycamore quantum computer had completed a task of 200 seconds, that would take a conventional computer about 10,000 years. However, IBM quantum level leads the world in quantum computing. This is nascent technology is widely expected to solve valuable problems that today's most powerful classical supercomputers cannot solve and never will. IBM Quantum makes real computing hardware, a tool scientists only began to imagine 3 decades ago, available to thousands of developers. Today, we have a good number of panelists who are distinguished pillars in this field. Let us educate ourselves on the theme and explore how this quantum technology can help us in our digital and comfort living. Thank you, sir.
And thank you, Mr. Chairman, for your beautiful and elaborate welcome address. I will introduce the theme for the people who are not thoroughly, versed with the advanced world of computing. Quantum computing is gradually becoming a practical solution where classical computer requires an enormous amount of time to solve the problem. Conventional computing is based on the classical phenomenon of electrical circuits being in a single state at a given time, where quantum computing is based on the phenomenon of quantum mechanics, such as superposition and entanglement. The phenomenon where it is possible to be in more than one state at a time. The specific areas are new drug design, enhanced cybersecurity methods, efficient traffic control, weather forecasting system, quantum interferometry, etc. It seems that in foreseeable future, we can expect the quantum computer will be available for common computational purpose as well. With this brief introduction, I think our chairman is beautifully illustrated and told about quantum computing. So now I would request Dr. G. Ranganath, Chairman, Committee for Advancement of Technology and Engineering, IEI, to propose his address.
Thank you, Engineer Ramachandran Chakrabarti, sir. Responsible as a moderator, as well, Joint Honorary Secretary of West Bengal State Center, doing a good job in the evening. In absentia, the President of IEI, Dr. H.O. Thackerayji, and Vice President Sandeep Dey, Chairman of ETDB, Girish Mundada, good friend in the Council, West Bengal State Chairman, Dr. Nirmal Kumar Das, Honorary Secretary of West Bengal State Center, Raju Basak, the most important speakers of this today program, Madam Munmun Chakrabarti, as well as Sanjay Kumar Chaudhary. Both are coming from the CDAC, a real expert from the field of quantum computing, who are going to throw a light on today's topic. The convener of this wonderful program, good friend of me, Chanchal Chakrabarti, is not only keeping big library behind him, he is keeping good network in bringing the experts to the topics. That is the proof of today, that he is bringing a good 2 experts on the CDAC for today's topic. All of the committee members of West Bengal State Center and attendees, almost all more than 40 attendees are there. Attendees, good evening to all of you. Let me not talk on the topic, because being I am a mechanical engineer and talking on computer computing in front of either Madam Munmun Chakrabarti or otherwise Nirmal Kumar Das, I may be small, I will become very small, because there is a topic. Of course, it is a very, very important topic. But here I want to emphasize The West Bengal State Center, after Nirmal Das has taken a chairman of the center, the front runner in conducting good number of activities, particularly technical activities, webinars and seminars and symposiums. So my heartfelt greetings to Nirmal Das ji. We are so happy that we are together working in the council as a council members, and you are giving a good service for the West Bengal State Center, and taking these webinars really wonderful, where the people from across the globe they can come and they can participate. It's not so easy in seminars and symposiums, but webinars is that. So you have taken webinars in almost all disciplines for the past 3 months. I am observing. Not only as a CATA chairman, as a colleague of the council, I am very happy to greet you, Nirmal Das ji. My heartfelt greetings to you and entire team members. Certainly, today's topic, it is very, very important topic, and it's a hot topic, quantum computing. And 2 speakers are going to give good importance for that. And bringing these 2 speakers, I have to thank our convener, Chanchal Chakrabarti ji, who has taken right initiations, and the elderly person, or Ramchandra Chakrabarti ji, Joint Honorary Secretary, is doing a moderator, means today's program is going to be wonderful. All attendees are going to get good benefit out of it. With this, I wishing all of you all the best and thanking the West Bengal State Center. Make me to be with all of you for today evening. Let me thank all of you and good evening to all of you.
Thank you very much, sir.
Sir.
Thank you, sir.
I think our president is not there, vice president is not there, Mr. Mundada, Professor Mundada also not available. So I directly go to the discussion. I will introduce the experts today and the moderator. We have the first panelist, Munmun Chakraborty ma'am. Ma'am has done her MCA from WVU Tech. After having graduated in mathematics, she is working as joint director in CDAC. Now, during the last 16 years, her area of work is image processing and computer vision. Recently, she started working in quantum domain. She is executing a project on quantum sensing funded by MEITI. We have the second panelist, Sanjay Kumar Chaudhary. He is working as a joint director in CDAC. Kolkata. He has 29 years of work experience. He has worked in the domain of artificial intelligence and machine learning, natural language processing. Currently, he is working in the area of quantum technologies. We have moderator this evening, Chanchal Chakraborty. He is BE MBA, having 35 plus years of professional experience in telecom and IT. Worked with flagship companies like CSC, NTPC, Department of Telecom, BSNL, Aircel, Uninor, and Reliance Jio. Presently, he is working as Vice President Technology of Reliance Jio. Wide experience in planning, design, procurement, installation, and maintenance in all fields of telecom. Participated in several national and international seminars, including GSM Congress at Cannes, France, and Berg for international roaming. He has received different accolades, including the Vishisht Sanchar Seva Award from the Ministry of Communications, professionally associated with IEI as a fellow member and IS International Society of Automation USA. A team player and love to serve society to the best of his ability. We started this monthly webinar in the last June, last year. So this is our 12th session. We could not do the session in April because of the election in Institute of Engineers. Now I request Chanchal to take charge and conduct the session.
Thanks, Ramda. Thanks all the dignitaries and the august audience of this evening. Now today we'll be having the wonderful journey of quantum computing, which will be narrated by our honorable speakers, Munmun Chakraborty, Joint Director, CDAC, and Sanjay Chaudhary, Joint Director, CDAC. So we'll request ma'am to start the session. The audience is now all yours.
Thank you for the introduction. Good evening, all the attendees present here. Hello, my screen is visible.
Screen is visible, ma'am, but your content has not started coming.
Now it is visible.
Yet to be.
Not yet.
It's not visible. My screen is not visible.
No.
No, ma'am.
Your screen is not visible, ma'am.
Just a minute. Is it visible right now?
No. No. It has not come.
Just a minute. Why it is showing screen sharing has paused? It is showing that your screen sharing is paused. Yeah. It is not resuming. Is this from your end?
Just a
Not
moment.
exactly.
Yeah, it is showing resume share. It is paused.
It is not. You cannot share your screen.
I think ma'am is having some trouble in sharing the screen. Can
Just a moment.
Just a moment. It is showing stop sharing. To disable. Oh, এটা নীলটা। এখানে দেখো তো stop sharing.
No, panelist sharing is enabled.
New Microsoft PowerPoint এই লাস্টে উপরে লাস্টে হ্যাঁ এইটা screen sharing is paused.
No.
It is stopped from your end, I think, because it is showing.
Oh, here it is showing that your name is showing and telling that has started screen sharing.
Yeah, from my end it is started. From your end it is stopped.
You are viewing Ms. Munmun Chakraborty joined this thing, director SIDAX screen.
এটা বন্ধ করে দিয়ে আরেকবার অন করবে? বুঝলাম হচ্ছে না।
Chanchal, do you have the latest presentation? Can you share your screen? Ma'am can.
No.
No, I don't have the latest.
Okay.
She has updated something.
If there is a problem, you can email to any of us, Chanchal or me. You can. It's better to Chanchal because he'll be moderating.
ওটা দেখাচ্ছে না।
তুমি বলছো একটু ওনাকে ইমেলে শেয়ার করো।
ইমেলে শেয়ার করব। তুমি আগে দেখো টা হয়তো।
You have to open the screen. I think you know definitely. And then share the screen.
একবার বেরিয়ে গিয়ে ঢুকে করবে।
একবার বেরিয়ে ঠিক আছে।
বেরিয়ে যাও।
Mr. Chanchal Chakraborty, you can just for a test case, can you share your screen and see if our system is okay?
Okay. Is my screen coming?
Yes. Your screen is coming. Yes.
Okay.
Yes. You can stop sharing. You may stop sharing. Please.
Yeah. I did it.
Yes, yes. Now ma'am can share and see.
Your screen sharing
Okay, that was
is
it.
paused.
Paused. Why share screen is paused?
Somebody, some other people is sharing. Follow that.
Hello?
Oh,
Some
no.
other person is sharing. It is showing that screen is paused. Share screen is paused.
No, no. Because
nobody-
I asked Mr. Chanchal Chakraborty to a test case to share his screen, and it was working there. And now it is showing that you are viewing Miss Munmu Chakraborty's screen.
It is showing now.
No, it's not coming.
It is showing
If you are having any problems, so what you can do is that you can share with me so that I can share from my end. If you are facing the trouble.
Hmm. মেলে পাঠাবো তারপরে হবে। কিন্তু সেটা আমার কন্ট্রোলে থাকবে না, কিন্তু সেটা আমি কন্ট্রোল করতে পারবো না তো। কিন্তু এটা কেন হবে? I don't know why it is happening, because this is the first time I have facing this kind of thing. Why it is showing that my screen has been stopped? Hello, I have sent the mail.
Ma'am, you have sent it to Mr. Chanchal Chakraborty.
Yes.
Oh, okay.
Hello? Hello?
It is showing, ma'am.
It's showing. You make it full screen. Make it full screen.
Yes.
Yes, yes, it is showing.
Now it starts showing.
Yeah, you make it in power presentation mode.
Make it presentation mode. In the bottom.
Yes, sir.
Yes, yes. Just wait.
PowerPoint.
Mhm.
First, we'll share the PowerPoint. I have, sir.
Oh.
No, no. ওপরেরটা। হ্যাঁ,
Right.
হ্যাঁ।
Yeah,
Yeah.
yeah.
Hello? Now it is
Yes.
visible?
Yes, ma'am.
Yes.
Now,
Yeah, yeah.
Yes, it's visible. Right. You can now start.
Sorry for the inconvenience caused.
No issue. Start.
Thank you. So, well, I have worked mostly in the area of image processing and pattern recognition. Right now, CDAC has started working in the area of computer computing in mission mode nationwide. In Kolkata Center, me, my co-speaker Sanjay Chaudhary, both are working in this area for few years. Recently, we bagged a project from MEITI, as said by the convener, on development of quantum sensor for detection ultrafine trace element in water like arsenic, heavy metals, etc. Today, I will present here the knowledge I have gained from this exploration. After completion of our presentation, we can discuss on queries which will enrich both of us, I believe. So let's start the session. Yeah. So 21st century is going to be the computing age. Have a look on generations of computers over years. First generation computers was large and limited to basic calculations. They consisted of largest device like vacuum tubes. Physical methods using punch card, paper tape, and magnetic tape were used to enter data into these computers. Example of first generation computers include ENIAC, UNIVAC, etc. The input method of this computer was a machine language known as 1GL for the first generation language. Second generation of second generation computers were more reliable, and in place of vacuum tubes, it used transistors. This made them far more compact than first generation computers. In these computers, primary memory was stored on the magnetic course. Examples of this generation computers include IBM 1620, etc. The input of these computers was higher level language like COBOL, Fortran, etc. Third generation computers are differed from first and second generation, that it used integrated circuits. And integrated circuit is a small device that can contain thousands of devices like transistor, resistance, and other circuit elements that make up a computer. Example of these generation computers are IBM 360 series, Honeywell 6000 series, like that. Input language for these computers were COBOL, Fortran 2 up to Fortran 4, Pascal, then Algo, etc. Fourth generation computer used VLSI technology, that is very large scale integrated circuit technology. Therefore, they were also known as microprocessors. These circuits had almost 5,000 transistors on a very small chip and were capable of performing many high-level tasks on computers. Examples are Star 1000, DC-10, like that. Computers used here were C, C++, DBase, etc. And fifth generation computers, that is present days, these are extremely reliable and employ ULSI, that is the ultra large scale integration technology, and are used to develop AI components. Methods of input include here is high level language like Python, R, C#, Java, etc. And examples are Intel P4, i3, i10 processor, AMD Athlon, etc. So the transistor in computers are small as we can make them with existing technology. IBM's tiniest computer is smaller than a grain of rock salt. So the new possible solution at the atomic and subatomic level in a field known as quantum computing. In 1927, at 5th Solvay conference in Brussels, 29 eminent scientists attended to discuss the foundation of newly formed quantum theory, which shook the world. We can say light has wave property as they interfere with one another. Sometimes they build the wave up and sometimes down. If we look for their particle property, the photoelectric effect tells us that photons are quantized. The particle property of light thought by Isaac Newton, he thought light was composed of particles that were too small to detect individually. Huygens, who was contemporary of Isaac Newton, suggested light travels in waves. In 1801, a physicist in England, Thomas Young, performed an experiment called Young double slit experiment, which I will elaborate later, that showed light behave as a wave. If we go through the properties of light, which were collected by scientists through years, we can see like this. Let's start with reflection. Does the particle model bounce off objects? Yes, for both the models. Refraction, could they bend as they move from one medium to another? Yes, for both. If we look for interference, can they interfere with one another? The particle model does not hold up, but the wave does. For diffraction, do they bend around objects? For particle, it's no, but for wave, it's yes. For polarization, when they're traveling in one dimension, can we use small slit to just limit the amount to go through? Wave can, but particle no. So wave model looks good. Finally, the photoelectric effect came around. If a certain metal plate is irradiated with light, an electron is ejected, which can be detected when it interacts with a positively charged wire or metal plate. The ability of light to eject an electron depends only on its frequency, not intensity. So if the beam was below a certain frequency, even a very intense beam with a lot of light could not eject an electron. But a beam above a certain frequency, the faintest beam possible could do this. Einstein solved this problem by extending the concept developed by Max Planck 5 years ago. Planck proposed the energy is not continuous, rather it is quantized. All energies are multiple of the smallest fundamental unit of energy, the Planck energy, which depends on frequency of light. Einstein extended what Planck said about energy and rationalized that light also mode of quanta, that is called photons. These are particles of light. In this parlay, the electron is ejected when struck by singular photon with sufficient energy. The energy of photon can be given by the equation equal to h nu. H is the Planck constant and having value 6.626 into 10 to the power minus 34 meter square kg per second. And nu is the frequency of photon. So we have duality of light. Light is both wave and particle. So Albert Einstein suggested dual nature of light in 1905. He suggested light, which is known as wave, is really a stream of photons, each of with a discrete amount of energy. Next puzzle came from Rutherford, a New Zealand physicist, popularly known as the father of nuclear physics. In 1909, Ernest Marsden and Hans Geiger, working for Rutherford, shot alpha particle on gold atoms. They were stunned to find that some bounce straight backward. Here, A is most alpha particles travel through the foil undeflected. B, some particles deflected by small angles, and C, occasionally an alpha particles travels back from the soil. This showed that most of the mass of the atoms is concentrated at the teeny nucleus. The model we see of atom with nucleus with orbiting like a miniature solar system is known as Rutherford atomic model. But there was drawbacks of Rutherford model. Rutherford atomic model could not explain how the moving electrons could remain in its orbit. Any charged particle during acceleration would give out energy, and while revolving, it would lose energy and eventually fall into the nucleus. This means that atom would be highly unstable, but matter is composed of stable atoms. Thus, major drawback of Rutherford atomic model was that it could not explain the stability of atom. Then Niels Bohr came to solve this puzzle. Niels Bohr, a Danish theoretical physicist, he was working with Rutherford. He pointed out existence of atoms with some modification of rules of physics. He proposed that an electron in certain special orbits does not emit light at all. Atoms absorb and emit light only when electron changes orbits, and frequency of the light depends on energy difference in just the way Planck and Einstein introduced. He fixed Rutherford's model and explained why atom emits only very specific color and light. Each element has a special orbit. Bohr's proposed model has three postulates, the early quantum theory of hydrogen atoms. First, the negative electron moves around the positive nucleus called proton in a circular orbit. All electron orbits are centered at the nucleus. Not all classically possible orbits are available to an electron bound to the nucleus. The allowed electron orbits satisfy the first quantization condition. In the nth orbit, the angular momentum ln of the electron can only discrete values ln equal to nh, where n equal to 1 to 3. This postulate says that the electron's angular momentum is quantized, denoted by Rn and Vn respectively. Rn is the radius of nth orbit and Vn is the electron speed in it. The first quantization condition can be expressed explicitly as me Vn Rn equal to nh. Third postulate was an electron is allowed to make transition from one orbit where its energy is to another orbit where its energy is. When an atom absorbs a photon, the electron makes a transition to higher energy orbit. When an atom emits photon, it goes to lower energy orbit. Electron transition with the simultaneous photon absorption of photon emits takes place instantaneously. So HF, it can be expressed as HF equal to EM minus EN. This allowed electrons transmission satisfy the second quantization condition. Then de Broglie came. Based on de Broglie's argument, nature is strikingly symmetrical. Light, classically explained by wave theory, possesses particle behavior as well. Particles also have wave behavior. So we have, according to quantum mechanics, we have equal to h nu. And as per theory of relativity, we have equal to mc square. So mc square equal to h nu. From this, we can derive P equal to h by nu. So particle property equal to wave property. From this equation, particle property and wave property can coexist in nature. Through this works, the framework of quantum mechanics build on the following propositions, like wave particle duality is reality. The behavior of subatomic particle can only be expressed statistically, or the state of quantum system can be represented by a wave function psi, such that psi equal to psi star. What is that? I will explain later. And it gives the probability of getting the particle at a particular space-time coordinate. The time-dependent equation of motion of wave particle can be expressed as a Schrödinger equation, where V is the potential energy and psi is the plane wave having equation psi xt equal to a into e to the power I kx minus omega t. This can be derived from the Hamiltonian of a system H, where for total energy of a system, we can write kinetic energy plus potential energy. The wave behavior of the particle admits superposition. We will show in subsequent slides that principle of superposition and a special situation of Schrödinger equation known as entangled state. These are the heart of quantum computing. Now have a look on how quantum computing is different from classical computing. In quantum computing, in classical computing, the message, the information is stored as string of bits, like 0, 1. 1 that is all, either off or one state at a time. Only two possibilities here. But on the contrary, in quantum system, one information, this here data can be represented using qubit, that is quantum bit, which is a superposition of two states. A state psi could be any position on the Bloch sphere between 0 and 1. What is the Bloch sphere? I will coming to that. In classical computing, the circuit behavior is governed by classical physics using logic gates. So here and or not, so normal classical gates are used. Whereas in computer quantum computing, quantum gates are used, and these have some special properties. Then in classical computers, complementary metal oxide semiconductor transistor are the basic building blocks of conventional computer, whereas in quantum computing, QUID or superconducting quantum interference device are the basic building blocks. I can't explore this much, but this is in a nutshell. In conventional computers, data processing is done in central processing unit or CPU, which is consisted of arithmetic logic unit, processor register, and control unit. In quantum computer, data processing is done in quantum processing unit or QPU, which consists of number of interconnected qubits. So why quantum computing is so amazing? In 6-qubit quantum system, state vectors can move around 2 to the power 6, that is 64-dimensional complex space, which is a 64-dimensional sphere. That is, for a n-qubit machine, we can get 2 to the power n states at a time in a superposition time. Now, I am talking about qubit. Now, what is qubit? A bit of data is represented by a single atom, that is one of the two states denoted by 0 and 1. For a spin-up particle, this is a spin up and spin down. A single bit of this form is known as qubit. A physical implementation of a qubit could be used the two energy levels of an atom, an excited state representing 1 and the ground state representing 0. So in Dirac notation, psi is a column vector denoted as psi. This is called as psi-kate. Psi dagger is a row vector denoted as bra psi in Dirac notation. The bra represented row vectors and denoted in this way, whereas kate is represented in this way. Then psi-kate, that is a unit column vector called as kate vector. Psi dagger is obtained by applying complex conjugate to the element of the transpose of psi. That is, we can get psi after applying transpose to the after applying the conjugate to the psi vector, then we have to take transpose of that complex conjugate. Bra vector and kate vector, when put together, they form this bracket, which is nothing but the inner product of vector psi with itself, and which is identity vector. So this is the metric representation. Here, bra 0 can be represented in a row vector, whereas kate 0 can be represented as a column vector. Similarly for 1. A single qubit can be forced into superposition of two states denoted by addition of two state vectors, 0 and 1, with probability amplitude alpha 1 and alpha 2. This alpha 1, alpha 2 are complex numbers, and the square of its sum is 1. A qubit in superposition is in both the states 1 and 0 at the same time. This is very important. Using a 3-qubit register, the psi vector can be represented in this way. Now, important topic is the Young's double slit experiment. This is the heart of quantum computing. I can say the light launched from S0 is incident on two slits S1 and S2, which are equidistant from S0 and have same frequency. A pattern of interference fringe on the screen is then produced by the light emanating from S1 and S2. All slits are assumed to be so narrow that they can be considered secondary point source. The sources S1 and S2 are said to be coherent. By coherent wave, we mean the waves are in phase or have a definite phase relationship. These are shown the pure constructive interference and pure destructive interference. Pure constructive interference is obtained when identical waves are in phase, whereas pure destructive interference occurs when identical waves are exactly out of phase, that is shifted by half a wavelength. So what conclusion we can derive from this? Young double slit experiment gave definite proof of the wave character of light. An interference pattern is obtained by superposition of light from two slits. This superposition we can explain by using Schrödinger cat. A cat is put in a box with a poison, bottle of poison. So it can be dead or it can be alive. So there is, when we open the box, either it will alive or it can be dead. There will be two possibilities. But in quantum mechanics, quantum theory, till we measure or till we open the box, the cat may be in both the way at a time. That is, it may be dead, it may be alive with a probability of 50%. So what will be the state of the cat? If psi is the state of the cat, either it will be psi dead or it will be psi alive with a probability amplitude 1/√2. So getting dead is 50%, getting alive is 50% at the same time. The act of making measurement, that is opening the box, will collapse the superposed state into one base state. That is, either it is alive or it is dead. If we attempt to retrieve the values represented within a superposition, the superposition randomly collapses to represent just one of the original values. That is psi equal to alpha 0, 1 plus alpha 2, 1. Alpha 1 represents the probability of the superposition collapsing to 0, and alpha 2 is the probability of collapsing to state 1. These alphas are called probability amplitude. In a balanced superposition, alpha equal to 1/√2, that is, probability will be half, that is 50% probability. Relation among the data. This is important entanglement. Entanglement is the ability of quantum system to exhibit correlations between states within a superposition. We can entangle the two qubits such that the measurement of one qubit is always correlated to the measurement of the other qubit. That is, for the box with cat, it is always correlated. If I get him live, at the same time I can also get the cat as dead. So from superposition we got a phenomena called entanglement. Now we can repeat the same Schrödinger cat with two boxes. Now I have two boxes, each of with a poison bottle of poison. So now I have four possibilities. Either both are alive, either both are dead. If one is alive, the second box will be dead. If one is dead, the other one will be alive. Each incident will have probability 25%. Now using quantum theory, we can erase the first two options. That is, both cat will live and both cat will be dead. It can be erased. So now I have two options. If for one box the cat is alive, then for the other box it will be dead. And if for one box it is dead, then it will be alive. There will be two cat system where one is alive, will tell another is dead. That is, they are entangled. For the two box, if I measure on the first box, then I will determine what will be the output of the measurement of the second box. So they are entangled. The state of the cats are entangled. So there is mind-blowing property of entanglement. If I prepare entangled state with two boxes of cats and we take opposite end of the world, outcome of the experiment will be same. That is, two box will be entangled at all times. So at one part of the world, I open the box and I got a alive cat, then I will be sure that on the other part where the box is, and that if it is opened, the cat will be dead. They will remain in entangled state. So what is quantum computing? In a nutshell, quantum computing is a computing paradigm that exploits quantum mechanical properties like superposition, entanglement, interference, etc., of matter in order to do calculations. There are several technologies for this quantum computing, like superconducting loops. Google, IBM quantum circuits, they all support this technology. But PROS is fast working, built on existing semiconductor industry, but the concept is collapsed early and must be kept in very cold, that is minus 273 degrees centigrade. Trapped ions, IonQ support this. The good thing is very stable, highest achieved gate fidelities, but the problem is show operations, many lasers are needed. This is very slow. For silicon quantum dots supported by Intel, it is stable, built on existing semiconductor technology, but the problem is only a few entangled photons, entangled states are available. It must be kept in also cold. Topological qubit, Microsoft Bell Labs support this. They greatly reduce error, but the existence not yet confirmed. Then diamond vacancies. Quantum diamond technology support this. They can operate at room temperature, but difficult to entangle. So a quantum computer is a machine that performs calculation based on the law of quantum mechanics, which is the behavior of particle at the subatomic level. This is the picture of IBM quantum computer developed by IBM Q. There is another picture. This is developed by D-Wave, which is commercially available. It has 5,000 qubit system. Existing quantum technology. Gate-based quantum computers are available in IBM, Rigetti Computing, University of Bristol, University of South Wales. Then adiabatic quantum computer supplied by D-Wave. These are available in Google, NASA, University Space Research Association, etc. Different frameworks. Quasant, Qiskit developed by IBM, then SARC developed by Google, Forest, PyQuil developed by Rigetti, QSharp, Microsoft, Ocean, D-Wave. These are different frameworks for quantum computing. This is the circuit composer developed by IBM Q. Here, the main programming technique is based on circuit composing of the circuit. Everything based on gates. So we can play around this quantum circuit to get different measurements, different results. Usually, the elements of computations are data, operation, and results. So for quantum computation, data are qubits, quantum gates are operation, and operating the using quantum gates on qubits, we can get results as measurement. Data representation. As I said before, psi is a state represented by 0 and 1 kth vector. For a single qubit system, a state is a normalized vector in a Hilbert's vector space, which is with a basis of 2 elements that we denote 0 and 1. So have a look some mathematics. Hilbert space is a vector space with scalar product. For a d-dimensional Hilbert space, the vector can be represented as a column vector. So if A is a state, it will be represented as a column vector of A1, A2 up to d-dimensional AD, where A1, A2 are complex number and sum of the square of these amplitudes are equal to 1. Scalar product between A and B will be just inner product between A and B. So a single qubit states are pointed on a block sphere. This is a block sphere for 1 qubit machine, that is having 2 states, 0 and 1. For a higher dimension, it is not possible to display. So a state psi can be represented on this block sphere with cos theta by 2, 0 plus e to the power I phi sin theta by 2, 1 kth, where theta belongs to 0 to pi and phi belongs to 0 to 2 pi. Operations on quantum, operations on data. classically we use AND gate. So truth table will be like this: 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 0, 0, and 1, 1, 1. In these three cases, the first three cases, the information got destroyed. So based on the output, it is not possible to determine the input. That is, if I get the output 0, it is not possible for me to tell what was the input. Is it 0, 0, 0, 1, 1, 0, what? So this type of gate is not accepted in quantum operations. Each operation of quantum computation is performed by a quantum gate, and they must be reversible. Quantum gates are unitary operators, and it acts like rotation on the Bloch sphere. There are some property which it holds. If U is a matrix of complex number and it is a quantum gate, then U dagger must be U inverse, where U dagger is the conjugate transpose of U. U dagger equal to U dagger U equal to identity matrix. And quantum gates are Hermitian operator, that is H equal to H dagger. In addition to this property, the quantum gate must have this property also, that if H is a Hermitian operator, then you must following this relationship: U equal to e to the power IHT. Now, if psi is a single qubit gate, so it can be represented as a column vector alpha beta. So you need a quantum gate in single qubit can be represented with a 2 by 2 dimension matrix ABCD. Now, following the property of unitary matrix, if ABCD is represented by U, then its complex conjugate, that is U dagger, will be represented as A bar, C bar, B bar, D bar, where A bar, B bar, C bar, D bar are the conjugate of the complex number ABCD, and it will satisfy the relation, that is U dagger equal to I. The standard computational basis for a single qubit 0 and 1, and it will be represented this column vector. The X gate is defined by this unitary matrix 0, 1, 1, 0, and its operation will be, if it applied on 0, it will transform to 1, and if it is applied on 1, it will be transformed to 0. Then a Z gate, the matrix notation is 1, 0, 0, 1. If a Z gate is applied on a, it is wrongly denoted here. If a Z gate is applied on a 0 state vector, it will remain same. But if the Z gate is applied on 1, it will be it will get a flip, and it will be -1. Then a very important gate known as Hadamard gate. The matrix notation will be 1 by √2, 1, 1, 1 minus 1. The speciality of the gate is it will transform the state to a superposed state. That is, 1 will be transformed in a superposed state of 0 plus 1 by √2, which is represented as plus gate. And if it is applied on 1, it will be transformed to 0 minus 1 by √2, which is minus gate. There is another gate, Y gate, where matrix representation is 0 minus I 0. These three gates X, Y, Z are called as Pauli gates, and also represented as sigma Y, sigma X, and sigma Z. Now, if I take a input vector psi as alpha 0 plus beta 1, if X gate is applied on that, output will be beta 0 plus alpha 1. If Y gate is applied on the same state, output will be minus I beta 0 plus I alpha 1. If Z gate is applied on the same vector, output will be alpha 0 minus beta 1. And if Hadamard gate is applied on this state vector, the output will be a superposed state of alpha plus beta by √2 0 k plus alpha minus beta by √2 1 k. And if we can reduce it further, and we can, after simplification, we can derive it to alpha plus gate plus beta minus gate. There is important relationship among them: X square equal to Y square equal to identity matrix. Another thing, two Hadamard gates can be used in succession and they can be used as a NOT gate also. Universal set of quantum gates. TH and C0s are called universal set of quantum gates. I have already detailed the Hadamard gate. Now what is T gate? T gate gives the target state to a flip to a rotation 45 degree on the Bloch sphere. The matrix representation of T gate is 1, 0, 0 e to the power pi by 4, whereas S give the target state vector to a rotation of 90 degree on the Bloch sphere. There are many more gates, quantum gates, and using like X gate can be used in succession with Hadamard gate, then Z gate, then H gate. So in quantum circuit, quantum composer, we can play around these gates to get different type of magical results. Now I am coming to 2-qubit state from 1-qubit state. 2-qubit state can be represented in bracket notation denoted by 0 tensor product 1 or 0 ket 1 ket or 0 1 ket. The matrix representation will be like 0 1 matrix representation. After the tensor product will be 0 1 0 0. So basis state for 2-qubit states are, as I told before, 2 to the power n, that is 2 square equal to 4 state 0 0 0 1 1 0 1 1. So this is the another part component of the universal gate, that is C0 gate. It is a 2-qubit gate. Here for the 2-qubit, first qubit is act as a control qubit and the second one is a target qubit. So if the first qubit, that is the first qubit is 0, the target qubit will be remain unchanged. But if the first qubit, the control qubit is 1, the target qubit will be get a rotation. It will be flipped to 180 degree on the Bloch sphere. So this is the circuit for the C0 gate. Now how it works? If the input state is 0 0, the control qubit is 0, target is 0. It will remain same 0 0. If it is 0 1, target control bit is 0, target is 1. It will be 0 1. But if the target is 1 and the control qubit is 1 and the target qubit is 0, it will flip the target qubit, that is 1 0 will be transformed to 1 1. For the if the target is 1 and the control is 1, it will be transformed to 1 0. This is a matrix representation of C0 gate, and it can be written in this way also. How to make base state using C0. Now what is base state? Base state is a set of entangled states. That is beta 0 0, beta 0 1, beta 0 0, that is 1 by root 2 0 0 plus 1 1. Beta 1 0 is 1 by root 2 0 0 minus 1 1. Beta 0 1 is 1 by root 2 0 1 plus 1 0, and beta 1 1 is 1 by root 2 0 1 1 1 0. So these are entangled states. So is there any other state other than this entangled state? Yes, there are product states. So where the state cannot be separable, that is called product entangled state. But where the states can separate, these are called product state. The condition is if psi is a state ABCD, it is separable if and only AD equal to BC. Now how C0 gate works here? To get this base state, suppose the input state is 0 0. Now for the control bit, Hadamard is used and it transformed to a superposed state. Now this superposed state is act as a control bit and it will work on this target bit and it will transform to 0 0 and 1 1, which is a base state. That is beta 0 0. There is maximally entangled state, that is triplet state and singlet state. Triplet state are called beta 0 1, beta 1 1 and 0 0. These states are called maximally entangled state. And another, this singlet state, this is also a maximally entangled state. There are several areas of application like artificial intelligence. Quantum computers could empower machine learning by enabling artificial intelligence program to search through these gigantic data sets, and new algorithms can be developed Drug discovery with quantum computers, we can create, stimulate, and model new molecular structure helpful in the area of new drug discovery. Optimization with quantum computers, we could able to handle almost innumerable permutation and combination. We could advance system design and analysis in massive ways. Then cryptography, quantum cryptography technique can enhance the security of the communication, unconditional security, and sniffing detection. In financial service, quantum computing could be used to find new ways to model financial data and isolate key global risk factors. There are several applications of quantum computers, which is not explained in a very stipulated time. So among these, I will explain a single technique that is called quantum teleportation. What is teleportation? Teleportation is telecommunication plus transportation. That is teleportation. The act of traveling by an imaginary very fast form of transport that uses special technology or special mental powers, or of causing someone or something to travel in this technique. This is a dictionary word, dictionary meaning of teleportation. But it is available, this can be possible only in science fiction. But in quantum computing, now scientists prove that it is possible. What is quantum computation? Quantum teleportation. The idea is Alice and Bob are two separate entities. Alice being a sender of a message and Bob is the receiver. It is not possible to simply make an exact copy of an unknown quantum state and give it to Bob. That is, the theory, no cloning theory prevents this. As a result of this, Alice cannot simply generate a copy of psi and give the copy to Bob. So what she will do, Alice and Bob, they will share an entangled pair of particles shared by a third party known as Telamon in IBM Qiskit. After that, Alice apply a CNOT gate and then she will use a Hadamard gate. Then Alice measure her pair. Alice contact to Bob on a classical communication channel and tells him about her measurement result. Given that information and a measurement on his behalf of the entangled pair, Bob is able to work out on the original unknown state, which is what has been teleported. How it is possible in quantum circuit? Suppose chi is the state alpha 0 plus beta 1 shared by Alice, and this entangled pair beta 0 0 is shared by the Telamon. Now Alice will apply the CNOT gate and it will generate the state psi. Then psi will be generated as a tensor product of chi and beta 0 0. After this, on psi, Hadamard gate will be applied and it will generate a state psi. This is the combination of four bases 0 0 0 1 1 0 1 1. So after measurement, we can get three possibilities. It will collapse on three possibilities. Either it will collapse to 0 0 0 1 1 0 or 1 1. So based on from these four possibilities, I am taking this 1 1 possibilities. That is 1 1 having the probability alpha 1 minus beta 0. How to get the original result, that is chi alpha 0 beta 1. After getting this, Bob will apply first alpha on this alpha 0 alpha 1 minus beta 0. He will apply X gate. It will generate alpha 0 minus beta 1. Then he will apply X gate. After that, he can able to measure the after measurement, he will able to get the original copy which Alice shared with him. The concept of quantum teleportation is a photon cannot be split. A quantum state of single particle cannot be copied. Measurement destroys or alter a quantum state. Security guaranteed by fundamental laws of physics, still limited by the speed of light. Quantum teleportation could mean more secure communication. So we are not talking about beam up Scooty that from Star Trek. The experiment didn't involve transmission of physical objects, only quantum states. The system also cannot be used for instantaneous communication. Still, it is limited by the speed of light. In fact, it requires a second traditional communication channel in order to work. It starts with two entangled particles, two photons, for example. It is like having only two copies of a book. Alice and Bob, each will get one copy. Alice opens her copy of the book and she can see the table of contents. If she then sends a message to Bob and tells him what the table of content is, he can then read the book. But if Bob opens the book without Alice telling him about the index, it will be total mess. He needs the index to make sense of the information. Since there are only two people in the world with copies of book, when Bob reads the information, he can be sure that nobody else has it. But how does Alice send the table of content to Bob? By any means she likes. She can send by email, by telephone. The second communication channel is here bound by the standard laws of physics. So, however, it works. Quantum teleportation could mean more secure communication, and it can be used in a technique called quantum key distribution. A joint China-Austria team has performed quantum key distribution between quantum science satellite Messius and multiple ground stations located in China. Such experiments demonstrated the secure satellite to ground exchange of cryptographic keys. Using Messius as a trusted relay, a secret key was created between China and Europe at a location separated up to 7,600 kilometers on the Earth. Another application is commercial QKD system, which is fabricated by ID Quantic. It is also available commercially. So technology could also have other applications, including quantum computers and quantum sensor. Now, my co-speaker, Sri Sanjay Chaudhary, will explain on quantum sensors. So, thank you.
Thank you very much, Madam Munmun Chakraborty. Now I'll invite co-speaker, Mr. Sanjay Chaudhary, to elaborate on quantum sensors. Mr. Chaudhary.
Yes. Yes. Let's try. Is the screen visible?
Yes, it is visible.
Okay. Okay. I'm starting this time.
Sir, you please make it full screen.
So already it is good afternoon, all the dignitaries present, and good evening to all. So how much time I'm going to get for this particular session, sir? It is almost 7:20.
No issue. You can
No issue?
continue up to 7:50.
Up to 7:50. Okay.
Yeah,
Please,
7:45, 7:50. After that, we'll be having question answer session.
Okay. Most
So please make it full screen.
most probably, yes. Most probably I have to skip some of the parts. Elaboration will be taken backstage. Well, I will try to condense the particular thing. So I'm starting the presentation. The flow of presentation is like this: statement of the purpose, standard techniques and the insufficiency of the standard technique, our experimental setup with small description of the parts, theory behind the better measurement precision using quantum mechanical phenomena. That might take a bit amount of time that requires your attention. Statement of experiment, spontaneous parametric down conversion SPDC for generation of single photon, which is a quantum mechanical phenomena, and Hong-Mendel effect, which is another quantum mechanical phenomena to be generated for getting the result of our experiment, and final measurement setup. This is the plan of presentation. So statement of purpose, we are doing a particular experiment for measurement of contamination of water for arsenic and lead. And this part of West Bengal is infested with arsenic and lead contamination, as we all know. So that is a primary concern for measurement of those two things. And arsenic and lead can cause what not sort of problem: chronic lung disease, bronchitis, bronchitis, restrictive pulmonary diseases, vascular peripheral vascular diseases, hypertension, non-pitting edema of feet and hands. Most probably you have seen in the palms the blisters-like things of the people who are affected with this sort of arsenic present in water. Conjunctive congestion, weakness, and anemia, everything. So therefore, detection of arsenic and heavy metals in water is an important parameter in environmental and health issues. And WHO recommends that 10 microgram per liter of arsenic presence is maximal for safe drinking. So 1 microgram per liter is proportional to 1 parts per billion. So measurement of presence of contamination in water is basically measured in parts per million or in parts per billion. So in our case, it has to go up to parts per billion. Normal interferometric method can go up to parts per million method, but we can, using interferometric technique of quantum computation, quantum mechanics, we can go up to parts per billion. So, well, 10 microgram per liter is a standard recommendation, but mostly in West Bengal, we are living in the world where we get 100 microgram per liter of arsenic in the contaminated water. We are drinking every day those sort of things. So that is way much beyond the limited recommendation of the World Health Organization. So I am going to tell you the constructional setup of our equipment, the purpose of that particular setup. Then I will explain the parts if possible. And if possible, I will go into greater details if time permits. So this is the constructional part of, well, before that, let me talk a bit about conventional interferometry, the conventional method that is still today used to measure the concentration of some contaminated thing present in liquid. As my previous speaker, Munmun, has amply defined the interference of light, that is, two sources of light get interfered and on a particular screen produces some black and white band. That is called constructive or destructive interference. So we can get this sort of black and white bands if we present two coherent sources of light in front of a particular screen. And using this particular technique, see this construction of standard classical interferometric method, how it is done. We use a laser source which is coherent and monochromatic. We divide that particular source into amplitude division so that we can get two light paths. One is this and one is this. And if nothing is present in the light path, still you are going to get on the screen a particular fringe pattern like the first one, black, white, black, white, black, white, which is the current fringe, calibrated fringe pattern, where there is no, in the path, nothing is present. Only two straight light is going, coherent source of light, they interfere and produce a band pattern and all these things. Now think of this, if in a particular path, if we insert a glass ampule with some sort of liquid with contaminated substance, that particular insertion will produce a phase shift between two paths of light. Phase shift means that two paths of light will differ in reaching this particular screen in different amount of time. So there is a path length difference between two parts of light, and the path difference is going to create another phase shift, another particular band pattern like this, the second one, black, white, black, white, black, white, but not in exactly the same position as the before. The previous one is in different position. The latter one, where some liquid with contaminated thing has been introduced, the band pattern is formed in different positions. And by changing the contaminated liquid, the portion of the contamination, we can get this sort of band in different position. And we can clearly make a table of the concentration of the liquid and band gap position shift. The shift in the band gap position in one column and the concentration of the liquid in another column. And from these two columns, X and Y, we can create a graph. The graph mostly will be a straight graph, and given an unknown concentration of liquid, definitely we are going to get a fringe pattern here. And from that unknown fringe pattern, we can define how much shift that particular fringe pattern has got. And from that particular shift, if we go to the curve, we can do the regression techniques. And from the graph, for the specific reference pattern change, we can get what sort of concentration we should get for the unknown liquid. So that is a standard classical interferometric method. But where lies the limitation? The limitation is that if we keep on decreasing the contaminated portion in the liquid more and more, and make the precision ultra fine, the concentration becomes so low that there produces a band gap, but the difference in the band gap is so slow and so small that normal any device cannot measure that particular shift, how much shift that has particularly caused. So there is no upper bar placed by the light that restrict us in making more and more precise measurement, but the measurement device's accuracy places a bar so that we cannot go beyond a particular concentration limit through classical interferometric method. So how quantum world has given us the advantage, let us discuss this particular thing and what is the management that we are making in our device. So one thing you must remember throughout the discussion, that insertion of this liquid inserts a phase difference between two paths of the light, inserts a phase difference, which is difference of the path length. So calculation of this particular path length, that is the phase difference, is primal to the experiment. That has to be very accurate. So phase difference measurement to the accurate limit is our prime goal. How far accurately we can measure the phase difference between two paths of light. So let us see. So this is a schematic representation of the our device configuration. This is the laser source. The laser source consists of 405 nanometer laser. This is a polarizer that polarized the laser source, which is called a pump source, in a particular direction, either horizontal or vertical. There is a lens L1. That particular thing focuses the pump into the crystal. The crystal is of type B bow, bismuth barium borate. This is type 2 crystal. There is another crystal known as type 1 crystal. So we will discuss that if time permits. So the particular light, coherent source of light that is coming from the laser, monochromatic, that falls on this particular crystal. And as this particular crystal shows nonlinear behavior, this particular nonlinear behavior breaks a particular photon into two photons of wavelength double and frequency half. So wavelength of these two particular photons that has been created after the type 2 conversion is 810 nanometer in wavelength, but the frequency is half of this particular incident pump laser. And there is, after that particular thing, a half wave plate has been inserted in one of the light path, and the photon beams are inserted into optical fiber. This particular zone up to this half wave plate is one
But your
portion.
slides are not moving. You are still
Slides
on the
are
first
not-
slide.
Slides are not moving.
I have not moved the slide.
No.
Oh, sorry.
I
We
have
are
not
on the
moved-
same slide. That's why I'm telling you.
I have not moved the slide. I will move after some time, right?
Okay.
So,
Thank you, sir.
so okay. So this particular up to this particular half wave plate, there is a particular portion of the device which is used to produce single source of photon. That is, do these two things, single source of photons. After this particular thing, that is called the sensory region, and this particular sensory region is used to create another quantum effect, which is called quantum entanglement, right? So how quantum entanglement will be produced, that will be discussed later. But let me discuss what is happening. This particular beam of photon, is going into the fiber optical section of this particular thing, and this beam of photon is going into the fiber optical section of another section. So two things, there are two fiber optical section. Those two fiber optical section are bent and joined together in this particular fashion. The U portion of this particular fiber portion and this U portion of this particular fiber portion touches each other, and they are being separated again. And like this, the photon beam goes out. So in this particular area where two fiber optic beams touches together, there the entanglement of the photon happens, how I will explain, and the entangled photon passes through this particular optical fiber, and they're collected to a particular device called single photon counter module, SPCM. The single photon counter module counts how many photons has been reached over there, and the output of the single photon counter module goes to the coincidence counter. That is how much coincidence of these photons has been occurring in a particular instance of time. And if we can get hold of the count, then we can generate this sort of graph. This particular graph, keep in mind, this particular graph looks like this, which is known as Hong-Wu-Mandel graph, which is another quantum effect that is taking place due to this sensory region where it is happening. So these are the schematics, and this is the overall representation of the scheme. So now I'm going to move, right? So I am going to move with the idea that I can explain that why using quantum interferometric method, we achieve higher accuracy level. That is the motto of my discussion. Please stick to me. It might be a bit lengthy, but if I am through with these things to you, my day is done. I am really getting through the message across the board that what I am trying to achieve. So we all know that photon is normally follows Bose-Einstein statistics, which looks like this: Ni is equal to Gi by e to the power something by kBt minus 1. So Ni is the occupation number of state I, Gi is the degeneracy of the ith energy state, epsilon I is the ith energy level, and mu is the chemical potential. Kb is the Boltzmann constant, and T is the temperature. We are not going details into this particular state of affair, but one thing, just to remember you, the previous physics class and all these things, if epsilon I minus mu is much greater than Kb by T, then this particular distribution terminates to Maxwell-Boltzmann distribution, which is normally followed in statistics of particles moving in random motion or something like that. So basically that is Maxwell-Boltzmann. Now, a peculiar thing happened around when quantum mechanics was getting formed. In 1926, Schrödinger, whose equation Moon has shown, the Schrödinger wave equation, first described a special state known as coherent state. Coherent state of light is such a state where it maintains particular phase among different wavefronts. It has different same wavelength and same energy. And in this particular state, I am skipping this particular portion because right now, due to the shortage of time, this doesn't make sense. And I'm telling you the moot points that in this particular state, that is in coherent state, the statistics of photons become Poisson distribution. So which was Bose-Einstein distribution previously becomes a Poisson distribution in coherent state, if we define coherent state like that. So what are the property of Poisson distribution? Let me tell you a bit aside. I'm going a bit aside. Don't look at the slide at this point of time. Poisson distribution we can see in the universe in different forms. Suppose it is raining outside and you are drawing a unit circle on the field. The number of droplets that particular circle is getting in an instant of time follows Poisson distribution. That is one. Poisson distribution follows birth and death process in an interval of time. How many childs are getting birth and how many childs or persons are getting death at a particular instant of time around the world, that follows Poisson distribution. Poisson distribution follows how many meteors that has hit Earth in the last 1 year, whose diameter is more than 1 meter. That follows Poisson distribution. And mostly Poisson distribution is followed by a particular photon beam, bunch of photons that is getting generated from a photon source like laser and hitting a photon counter. That follows Poisson distribution. So these are the distribution that follows Poissonian distribution, which is real life phenomena and all these things. And in this connection, I just want to tell you one story that all of us has studied electronics, electrical engineering, all these things. If a circuit, normal circuit with copper wire and batteries attached with 2 ends, carries current through that particular current loop, right? And because of flow of electron, there is current. So some sort of loss always happens in that particular circuitry. which is known as loss due to Joule heating, and which follows a particular criteria called Johnson-Nyquist criteria, right? That Johnson-Nyquist criteria gives some sort of heating loss, which is known as Joule heating. But there is some sort of another loss which is not very visible in the electrical circuit, which is known as short noise. That is a short noise. That is also a source of attenuation. But as we keep on moving in generating newer devices like PIN junction diodes, PN junction diodes, photodiodes, telecom instruments, fiber optical devices, and all these things, and our measuring instruments are getting more precise day by day, we can see this short noise present in the medium more and more. So short noise, we will come to what short noise is all about, but short noise limit is an effect due to the distribution, Poissonian distribution of light. We get a particular loss known as short noise loss. So there are two loss. One is heating loss and one is short noise loss. So short noise, we will come back. Now let us come back to the property of the Poisson distribution. Poisson distribution is an appropriate model if the following assumptions are true. If k is the number of times an event occurs in an interval, and k can take values 0, 1, 2. So k is discrete valued and integer valued function, right? So a distribution over k gives Poisson distribution. So Poisson distribution is a discrete distribution, not a continuous distribution, and it has a specific PMF, that is probability mass function. It don't have any probability density function. It consists of probability mass function. The occurrence of one event does not affect the probability that a second event will occur. Mutually exclusive, that we are going to say. That is, event occurs independently. The average rate at which the event occurs is independent of any occurrences of previous occurrences, right? We take it to be constant, but in practice, it may vary with time. And the last one, two events cannot occur at exactly the same instant of time. Instead, at each very small subinterval, either exactly one event will occur or no event is going to occur. So in a subinterval, either one event is going to occur or no event is going to occur. If that particular last statement is sticking a bell in your head, then you can discern that it is exactly the property of binomial distribution. So binomial distribution follows this particular property, and with no surprise that the limiting distribution of the binomial distribution is a Poisson distribution. So Poisson distribution is really arrived from the binomial distribution, and binomial distribution has this particular characteristics, which particular characteristics is also followed by the photons. So this is a Poisson distribution. This is a diagrammatic representation where lambda varies from 1 to 9. And what is lambda? Lambda is the average number of occurrences in an interval. Lambda is the average number of occurrences of what? Occurrences of the event that we are trying to measure. Lambda is the average number of occurrences in an interval. And one peculiar thing about Poisson distribution is that if the number of lambda increases, it naturally tends towards the Gaussian distribution. That is a normal distribution. So when lambda reaches 9, almost this pink curve shows like a Gaussian distribution, that is normal distribution. But what is the probability mass function of Poisson distribution, Px? It is e to the power minus lambda, lambda to the power x by factorial x. It is a distribution nature. And the mean and variance of this particular distribution, mu and sigma square, is both lambda. This is peculiar to Poisson distribution. No other distribution has this property. Then mean and variance are the very same. And the standard deviation is, as you know, square root of variance. It is square root of lambda. Now we are trying to define.
The slide is not moving.
I have not moved the slide yet.
Oh, actually, without slide becomes a little bit of difficult. Okay, sir, thank you.
So no, I have not told anything beyond the slide, sir. The
Okay,
mean
okay.
is lambda, the variance is lambda, and the standard deviation is lambda, root over lambda. If you can see.
Yes, yes.
Right. So, sir, are you seeing this particular slide? Poisson distribution?
No, not
No,
really.
no.
Not really.
Oh,
That is why I am telling.
slide name.
2 cross 2 coupler is showing the slide. Fiber couplers function.
You are in slide number 41.
41, yes.
Oh. देखो,
Slide number 41.
new share.
Sir, kindly go to presentation mode.
Yes.
If it is full screen mode, then I think it will be all right. Otherwise, it will be very difficult to follow.
Sir, what you are seeing?
Hello.
Sir, what you are seeing?
I'm saying, sir, please turn it into a full screen mode.
Which is full screen mode, sir?
At the bottom, if you see, just beside the 69%, just before that, one button is there. Simply click that.
Yeah, yeah. Slideshow option is there.
The
If you go
slideshow.
for the slideshow, then you
Yeah,
can.
yeah. Now you are putting it right. You just click it, it will come. Right.
What you are seeing?
It has not come so far.
इधर आओ.
Sure, sir.
Sir, on the top, there is several options, right? Reset design. Yeah, now it is all right. Yeah. Now it is full screen, but not in presentation mode.
No, the presentation is not available at this moment.
I'm requesting Engineer Chanchal Chakraborty, if you have the copy of the presentation, then you can show.
No, they are having the presentations actually.
Okay, sir. Okay, sir. Okay, sir.
So, if possible, then sir, can you share your video? I'm stop sharing.
Sir, if you are facing any difficulty, then mail the copy to Engineer Chanchal Chakraborty.
It has already been mailed.
Okay, okay, sir.
You have to make stop sharing.
Right. Either round.
Madam, just make stop sharing.
Right. Wait.
Should I again share the screen?
No.
Oh, no.
Yeah. Now it is coming.
Which slide you please tell me?
Okay. So, okay, sorry that things.
Is it this slide?
No, this after this.
Okay.
After this. Yes.
Okay.
Yes. Okay.
Right.
Yes. So, would you start? This is in presentation mode or what?
I got a PDF copy, so that is the only option.
Now it's all right, sir. You can start. I hope you don't mind, sir, because I am raising the question because somebody in the question answer session are writing that without presentation it will be difficult to understand. That is
Yes.
why, sir.
Yes.
Okay, okay. Thank you, sir.
Hello, Mr. Chanchal Chakraborty. Right now, I have mailed you both of our presentation.
1 minute.
That is in PPT. Sanjay. Yes.
1 minute. Just hold on.
Right. এতক্ষণ দেখতেই পেল না, এতক্ষণ বসে গেলাম, দেখতে পাই। ওকে, ঠিক।
Is it visible?
Yes, yes, sir. Perfectly.
Is it now okay?
Okay, sir.
Which slide?
So keep on moving. The same slide actually. That I have told all these things. Sorry that these things is so well. Skip this. After that, interferometric method I have told, right? I have told this particular thing. I have told the photon statistics, coherent statistics. I have told Poisson. Okay, let us start from here. Let us start from
Poisson
here.
distribution. Yes, sir.
Yes.
Yes,
So I was telling that coherent source of light follows Poissonian distribution that has been described by Schrödinger. And Poisson distribution looks like the left panel. Lambda is the number of events that occurs in a specific amount of time. So as lambda gets increased, the particular distribution of Poisson distribution takes the shape of a Gaussian distribution, that is normal distribution or Gaussian distribution. As the number of occurrences increases, that distribution tends towards Gaussian distribution. That is a property. So what is the probability mass function? Because I have already told that Poissonian distribution is a discrete distribution over integers. So probability mass function looks like e to the power minus lambda to the power x by factorial x. This is the probability mass function, and whose mean is mu, which is lambda, whose variance is sigma square, which is lambda as well. And this is the peculiar distribution where mean and variance all have the same value, lambda. No other distribution has this specific property. And standard deviation being the square root of variance, sigma is equal to square root of lambda. Next slide, sir. Next. So now we are defining a particular quantity called relative amplitude of fluctuation. Relative amplitude of fluctuation, don't forget this particular thing, which is standard deviation per mean. And this implies that how much accurate your probability distribution can be reached, how much accuracy your probability distribution can be reached, which is standard deviation by mean. In our case, standard deviation is root lambda and mean is lambda. So it is root lambda by lambda is equal to 1 by root lambda. This is the particular limit the Poisson distribution's accuracy can be reached. Keep in mind, lambda is the average number of occurrence in an interval. What's occurrence? Occurrence of the event. What is the event in our case? The event in our case is the number of photons that is getting emitted from the source, which is laser source, at an interval of time. The number of photons, if the number of photons is n, then n is the equivalent of lambda here. So if n is the number of photons that is emitted per unit time from the source, the accuracy of the measurement will be root over n by n is equal to 1 by root lambda. So 1 by root n is the accuracy if we use coherent source of light to measure something. So this is this particular thing. Next slide, sir. Next. So this particular limit has a name. This is known as standard quantum limit, which is known as short noise limit as well. Now I am going through these particular slides a bit slowly because it needs some sort of explanation why short noise and why Poisson distribution gives this sort of accuracy limit 1 by root n and how we can better that particular thing. In statistical experiment, such as coin tossing, fair coin tossing, if it is done many number of times, the throw will differ by only a tiny percentage. Say 10,000 times, the success of heads or tails is almost half and half, 50% and 50%. Varies 2-3 numbers here and there. But think of a particular experiment done in the following fashion, where we are tossing the coins, say 20 number of times. Now the variation of head and tail will be much more. It may be like 12 heads, 8 tails, or 15 tails, 5 heads. This particular distribution will follow if the number of trials is less. And you keep on this particular trial in a bunch and do all the experiment bunch after bunch. So what we are doing, 20 head and tail experiment, counting that particular thing, putting that experiment in a bunch. Then taking the coin again, doing 20 head and tail experiment, putting the count in different bunch. Again doing head and tail experiment, doing the count and putting the third experiment in third bunch. And we are making bunches of this particular experiment, one after another. So it is like the generation of electron from a source. It is bunch of quanta. So if we do that, the variation between the inter-experimental fluctuation of the accuracy varies a lot. That is being told that if an experiment with a few throws is repeated over and over, the outcome will fluctuate a lot. So now the fluctuation is not 50%, 50% all the time. There is an inter-module fluctuation. And from the law of large number, and from law of large number, which has been highlighted, I'm just reading it slowly. One can show that the relative fluctuation that we have measured before, relative fluctuation of amplitude, just before, the relative fluctuation as the reciprocal square root of the number of throws, that is the number of events, as a result of valid for all statistical fluctuations, including short noise. So short noise gives the relative fluctuation of amplitude as 1 by square root of n, where n is the number of photons that is getting generated from the source. So that is the statistical limit, and which can be arrived from the law of large numbers. Next slide, sir. Short noise exists because phenomena such as light and electric current consist of the movement of discrete, also called quantized. Here comes the quantization effect, like packets. So photons and electrons are generated like bunch of marbles, like packets, and consider light a stream of discrete photons coming out of a laser pointer and hitting a wall to create a visible spot. That is also is quantized thing. Next slide, sir. The fundamental physical processes that govern light emission are such that these photons are emitted from the laser at random times, but the many billions of photons needed to create a spot are so many that the brightness, the number of photons per unit of time varies only infinitesimally with time. So billions of photons coming at a single instant, we cannot see the short noise limit because due to the presence of law of large numbers and the property of Poisson distribution tending towards Gaussian distribution, this particular variation of distribution, which is short noise limit distribution, is not visible. But what if the scenario is changed like this? Next slide. However, if the laser brightness is reduced until only a handful of photons hit the wall every second, so situation has been different than the previous one. The relative fluctuations in number of photons, that is the brightness, will be significant, just as when tossing a coin a few times. We have shown that what is the effect that gets generated. These fluctuations are short noise, and this particular short noise. Next slide, sir. Next slide, sir. And this particular short noise places an upper bound in the measurement so that we cannot go beyond that particular measurement when coherent source of light is being used. Where short noise develops, short noise may be dominant, but the finite number of particles that carry energy of electrons or photons in an optical device is sufficiently small so that the uncertainty is due to Poisson distribution. Short noise generated due to Poisson distribution, we have discussed that particular thing, which describes the occurrence of independent random events, are of significance. It is important that it shows up in electronics, telecommunication devices, optical wave detections and all these things, waveguides, and fundamental physics. Here short noise is predominant, which places the maximum upper limit of calculation. Next slide, sir. Now it has already been discussed that due to the short noise limit, or which is known as standard quantum limit, the measurement precision is 1/√10, which is standard quantum limit. So is that all? Is that maximum limit that can be achieved using coherent source of light and quantum phenomena? The heartening answer is that no, it can be bypassed, it can be surpassed, it can be bettered. How? We are going to discuss that particular thing. The quest for measurement of schemes surpassing this standard quantum limit has inspired a variety of clever strategies, such as squeezing the vacuum, optimizing the probing time, monitoring the environment, and exploiting non-Markovian effects. So next slide, sir. So quantum mechanics places a fundamental limit on measurement precision called the Heisenberg limit, HL, which is beyond the standard quantum limit, which constrains how the precision of the parameter estimation improves as the total probing time T increases, or the number of photons that is used as a probe that increases. According to Heisenberg limit, the scaling of precision with T can no better than 1/T. As T increases, so the measurement precision decreases. And the precision scales no better than 1/n. 1/n, with total number of probes n used in an experiment. Total number of probes n. What does that imply? N is the number of photons that has been used to measure something. So each photon is acting as a probe. If we use n number of photons, our measurement precision is now 1/n. So previously, when we are using quantum source of light, coherent source of light, the measurement precision was 1/√10. Now, if we use Heisenberg state of light, which is squeezed nature of light, the precision measurement becomes 1/n, which is 1/√10 fold increment in the measurement precision. So we are gaining something in the precision. If we can create a state of light which is entangled, which is squeezed, and for noiseless system, Heisenberg limit scaling is attainable in principle by, for example, by preparing an entangled Null state of n probes. So this Null state needs some sort of explanation, and n is the number of photons. So if we can prepare this sort of state, we can better the performance measure than 1/√10, and we can reach up to 1/n limit. Next. So I should not go into this sort of discussion at this point of time. Most probably I should skip. Next. So how we can better that particular measurement? I will tell this, and most probably I am going to finish. I have to finish this discussion because I have overshot my time already. So think of the Heisenberg uncertainty limit. Actually, Moon has discussed in our present day scenario. We see that there are some sort of variables like position, momenta, energy, and time. Those are connected with a particular relationship, which is known as Heisenberg principle, where del x dot into del p, that is the measurement precision of position multiplied by the measurement precision of the momentum, cannot go beyond the limit of h cross by 2, which is the most upper bound of that particular thing. Now, in the quantum state of light, which is EM wave space, which is a phase and amplitude space of light, there are also two quantities which are bound by the Heisenberg uncertainty principle, and those two quantities are called phase and amplitude. The phase and amplitude in the standard condition, as we understand the phase and amplitude of the light, those are two things. So this is the particular relationship that exists. The measurement error of phase del phi and the measurement error of amplitude del A has an upper bound which is 1, right? So this is Heisenberg uncertainty limit that is being placed in the optical domain, that is an electromagnetic spectral domain. And the operators here are quadrature operators. That is a different story altogether. Second slide, sir. For quantum limited laser light with minimum uncertainty, del A is equal to del phi, and the light in a coherent state. Light is in coherent state. In the amplitude phase plane, the coherent state is best represented as a vector, as a stick, whose length and phase angle correspond to the classical amplitude and phase, respectively, while the ball at the end of the stick corresponds to the uncertainty. Next picture, I am explaining what has been told here. Picture, next slide, sir. So in the quantum mechanics, always we have been told that when we are talking about a particular state of affair, the state is represented by a vector that is a line with an arrow. So a particular light's condition, which is defined by phase and amplitude, is defined by this particular line. And the measurement error of phase is defined by a Gaussian distribution like this, px versus x. And the measurement error of this particular thing is phase, and this is amplitude, by the way. The amplitude side has an error distribution like Gaussian, and the phase side also has a error distribution like Gaussian. So this particular blob, circular blob, is superposition of two Gaussian distribution, which in the phase plane looks like a hat. So this is the measurement error, which is equal in both the direction of phase and amplitude. So this is called the coherent source of light, where measurement error in the phase and amplitude is equal. Both sides it is equal, which is called the coherent state of light. Now, the coherent state of light places an upper bound of error in measurement through the Heisenberg principle. But we can create something very interesting from this particular state. Go to the second slide, sir. The consequence of this uncertainty in amplitude and phase have a profound effect of our ability to use light to measure the position of a particle. Position means phase of a particle. Next slide. Next slide. We can create a particular state of light which is known as squeezed state of light. From the coherent source, we can create a source of light which is called the squeezed state of light. And see the left panel first. Here, the measurement error in the amplitude and the measurement error in the phase were same, Gaussian distributed and same amplitude. So it is circular in nature. But Heisenberg uncertainty limit has never told us that it is always has to be circular. It can be an elliptical thing, but overall volume of this particular thing should be within the limit 1. Because the particular limit was shown to be 1, for the circular it is already 1. But if we stretch that particular thing and make the circle a particular ellipse, the particular volume is remaining constant, but one direction is getting thinner and one direction is getting elongated. What it implies? So this particular direction is the direction of phase. The y direction is the direction of the phase, and the x direction is the direction of the amplitude. So phase direction is getting squeezed. So the error measurement in the phase direction is getting much more accurate. So we can measure the phase of the particular thing much more accurately because we have less variation in this particular direction. But at the cost of the amplitude measurement is getting elongated. So amplitude measurement will be varying more than the previous one. So at the cost of amplitude variation measurement will be greater, but the precision in the phase measurement will be shorter or smaller if we can make this sort of distribution of light, which is known as squeezed state of light. The squeezing meaning is only apparent because we are squeezing the particular light in one direction. This particular direction has been squeezed. So in the squeezed state of light, now the uncertainty of the measurement becomes, phase uncertainty of measurement becomes proportional to 1 by n. Previously, when we are using coherent source of light, which is circular in nature, here circle has been shown, the measurement accuracy is 1 by root n. Now, if we use squeezed state of light by some mechanism, which is really quantum mechanical in nature, now the uncertainty scaling of the measurement error becomes proportional to 1 by n, which is much better than 1 by root n. Because if n is 25, 1 by root n is 1 by 5, and 1 by n is 1 by 25. So the precision of 1 by 25 is definitely greater than 1 by 5. It is apparent. So if we can create this state of light, we can measure the phase, which in the very beginning we have told the measurement of phase is the main criteria of our attaining good result. Next slide, sir. So should I stop here? Because we have already 8.5 or 8.7, 8.10. So, well, this is the crux of the matter, that why quantum state of light can give us better measurement result. But how the experiment and all these things, we can take up the discussion in some other day if time permits. Definitely, there are lots of discussion that needs to be told. So if you permit that, we can take questions at this point of time. But if you think that we should stop at this point of time.
I think we can discuss this particular slide and then you can close.
Okay. So the present work of us that we have described propose highly sensitive device to detect ultra fine trace level of concentration using quantum optical sensor. The sensor works utilizing the quantum entangled state of photons that we have just described how to create the entangled state of photons, which creates a squeezed state of light. And through the classic experiment of Hong-Woo Mendel, this portion I have not discussed, I have not got time really. Through the classic experiment of Hong-Woo Mendel, HOM experiment that is called, which is quantum mechanical in nature, it is established that the interference of photon can be realized using 50-50 beam splitter. And as a, just to add something, this particular Hong-Woo Mendel produces something where the photons can be bunched together, because we know that photons bunch together and electrons get separated in the spatial coordinates. Because photon comes together, they remain in the same energy state, they are coalesced together, that is called photon bunching. And electrons in the opposite side, which follows Fermi-Dirac statistics. Actually, photon follows Bose-Einstein statistics, BE statistics, and the electrons, being fermions, follows Fermi-Dirac statistics, they anti-bunch. So we can create by Hong-Woo Mendel effect some state of electrons where two electrons comes together, get bunched and get squeezed, so that the particular state of electron is 2, 0, and there is another state of electron that is called 0, 2. So in totality, the particular state is known as noon state, which is 2, 0, 0, 2 state. And that particular state, if we can produce that particular state, we can measure the concentration of a particular liquid in much more precision than standard quantum limit permits us to do. So let us stop, no more discussion, otherwise time is really running out. So,
okay. So
okay.
Thanks, Mr. Chaudhary, as well as Madam Chakraborty. So we'll stop it here, and we'll be having subsequent sessions on some other sessions on some other day.
Yes.
And now what we can do is that we can summarize whatever we have so far discussed, is that we have made, the Madam Chakraborty has started with the evolution of the computers, and then we have come to the quantum state, and starting from the work of Max Planck, then Einstein, Rutherford, Bohr, who has made, Professor Niels Bohr, who has made the 3 postulates of early quantum theory of hydrogen atom, and then followed by the Louis de Broglie's work with the principle of duality, and then followed by the Schrodinger's equation, which had made the solid foundation of the quantum theory. And with this thing, we have discussed about the classical computing versus quantum computing versus bit versus qubit, the logic gates versus quantum gates, the CMOS technology versus superconducting quantum interference device like SQUID, CPU and ALU, which was used in the classical computing. Now you are utilizing quantum processing unit like QPU. And we have seen that in n qubit machines, we are having 2 to the power n states. So you can see that how many states are simultaneously existing. So we have discussed about the superposition theory, which has been explained by Schrodinger's cat theory. And then we have discussed about the quantum entanglement, where we have finding the states, superposition of both the states simultaneously, as well as whenever something is existing, then another is non-existing, and it is happening even at the long distance event that has been proven. So we have used the different technologies like semiconductor loops, trap dance, and silicon quantum dots, etc. And the different quantum computers have been devised by IBM and D-Waves and others, and the different quantum computing languages also got evolved. Now, we have also talked about the
Yes.
different kind of logic
Half an
gates
hour.
which are being utilized over here, as well as the different applications in artificial intelligence, drug discovery, optimization, quantum cryptography, financial service, and teleportation, which have been utilized nowadays. And later on, it will be leading to, the quantum key distribution, which will be instead whatever present KPIs we are utilizing, like the private and public key concept. So nowadays, that the blockchain technology will be under threat of quantum computing, because every 10 minutes, the blocks will be updated, and the computing power of quantum computing is so fast that it will be able to break that code. So the quantum, specifically the quantum cryptography is the most important thing, and which will be the presently appearing to be the ultimate cryptography appearing to be at this moment. Now, Professor Dr. Mr. Sanjay Chowdhury has talked about quantum sensors, which are very, very important. Specifically with a use case, he has talked about the arsenic and heavy metal contamination in water, which is having the different kind of diseases in the separate places. And the safe limit is the 10 mg per liter. And also he has told that whenever the photons pass through the light, it's passed through the contaminated liquid, so there will be a phase differences, and that will be there will be a path difference of the movement, and obviously that will be leading to the phase difference and the shift in the band gap, which will be from the graph with the regression technique. You can find out the solution. But if the band gap is so small, then the present equipment will not be able to grasp the thing. So we have to move to basically the particular concentration limit cannot be adjusted within the present setup. So the quantum sensors will be utilized with the help of the quantum entanglement, and it will be using the Poisson distribution, which is a basically a seminal work, and with the mean which is equal to lambda and the variance is lambda, where the lambda is the average number of occurrences in an interval. And here it will be basically the number of photons which are getting emitted from the source in a given interval, which is defining the accuracy. He has also explained about the short noise, which is basically giving the relative fluctuation, and that will be getting reduced if with the reciprocal square root of the number of throws of a coin or a dice or anything else. And that makes a statistical limit, which is basically the standard quantum limit. In the quantum mechanics, the limit is specified by the Heisenberg limit, and it is proportional to 1 by n, where n is the number of probes or the number of photons which are there, and that is basically given by the del A dot del phi, where the del A is the uncertainty in amplitude and del phi is the uncertainty in the phases, and that will be greater than 1, which is basically is given the noise in the laser placed in any electromagnetic wave. Now, it has been also shown that the phase and amplitude distribution is a Gaussian distribution in case of coherent state of light, and that gives a circular kind of distribution where the probability is inversely proportional to the square root of n. But in the squeezed state of light, which is given by the Heisenberg uncertainty principle, which gives the del phi, which will be inversely proportional to the number of probes, and that gives the phase direction is getting squeezed. That means the phase measurement is very, very accurate, and amplitude measurement is varying. So that gives the very specific phase. The phase difference is very, very accurate, and that gives the very specific measurement whenever there is a shift in the band gap. So with this thing, we are able to see that we are having a lot of use cases, and we can move ahead with this type of seminars for this type of whatever seminal works they are doing, and we'll be getting much more input from them. Now, with this thing, thank you, both the speakers, with your excellent speech. Now we'll be taking up some sample questions because the time is too limited. Mr. Tapan Kumar Banerjee has told the excellent presentation. Mr. Tapan Kumar Banerjee is also telling, I request madam to explain more and reading through a bit less to make excellent presentation. It's really very good, the presentation. Mr. Shekhar Kumar De is asking which technology is used in supercomputer. If madam, you can elaborate certain about this.
So actually, supercomputer is collection of. It is different than quantum computer, by the way. I mean, supercomputer technology used.
Absolutely.
So it is not quantum computer. So it is collection of smaller computing devices, and with GPUs and general purpose units, like different chips coming together and forming a larger and larger cluster of the things, because different supercomputer follows different architecture and all these things. Our supercomputer, right? So supercomputer is following the current paradigm of computing. So, but quantum computer paradigm is altogether different. So
yes, absolutely.
That is the point. But the technology that is being used by the supercomputer is that Cray XMP14 use array processor and all these things. So
yes.
Other computer follows different organization or something like that. Shared memory computation with distributed computing architecture, that is also one thing that has been followed at particular point of time, or memory sharing with different arithmetic processing unit that is clustered together to form a bigger and bigger cluster of computer. That is also a form of supercomputer that has come around in the early 90s and something like that. That has already been developed. So it is a different technique altogether.
Yes, absolutely.
Right.
Now we'll take another question by Jagdisha Chinnagudi. In image representation inside a quantum processor, which representation is better among FRQI, flexible representation of quantum images, NEQR, novel enhanced quantum representation, GQIR, generalized quantum image representation, QBIP, quantum Boolean image processing, MCQI, multi-channel representation of quantum images when you have used IBM or Intel processors.
So might be Moon might be telling something.
Let me explain one thing. Still, we have shown here only about quantum sensor, and it is not possible to touch every domain where computer quantum has application. So if you ask out of domain, then it is not possible to answer. However, I can tell one thing. In IBM QSkit, FRQI and NEQR has already implementation is there. So anybody want to explore image processing in using quantum computing,
IBM QSkit.
In IBM QSkit, he can explore. But between these two, I have not explored other. But between these two, NEQR is better, and the code is available in QSkit.
Okay, thanks, madam. And we'll take the last question of today's session. I think only one question is left out, two questions, or anyway, these are the almost same question. Please name major companies and institution in India engaged in quantum computing development. Another question has come from the same person. Which are the major international companies involved in quantum computing?
That has been already
been told. We have talked about D-Wave, IBM, all such.
Yes.
For the international companies, I already mentioned the technologies on which the companies are used. But for India, for Indian company, I can name some of them. There are IITs and IISc Bangalore. They are working on quantum computing institution-wide. But for companies, Boson Q, it is a Vilay-based company. The owner is Dr. Satyendranath Bose. This is a reputed company in quantum computing. Then quantum computing startup like QLab, it is also very famous. Then there is another QPI Tech Lab based on Bengaluru. And this is an AI-enabled quantum model generation platform they are using as a service. Then there is QNew Lab. This is also Bengaluru based and they work in quantum key distribution. Then there is Automat Key. Again, it is Bengaluru based and it has office in Los Angeles. Then Quantica Compute Echo, that is Chennai based startup. And finally, there is QRD Lab. This is Kolkata based. The lab is in Kolkata. And this actually work in capacity building, quantum research, etc. There is another company like Craze, they are TCG Craze, they are just started to develop. Still now this is not, there is nothing, but they are trying to do something, some initiative already taken there. So this is all about.
Thanks, madam. Now I'll invite Dr. Raju Basak to give vote of thanks.
Is it audible, sir?
Yeah, you are audible.
Thank you very much. Thank you very much for giving me the opportunity to propose the vote of thanks, especially Engineer Chanchal Chakraborty. So it is a customary, but anyhow, without vote of thanks, the program cannot be completed. It's my proud privilege to extend my sincere thanks and gratitude to all the distinguished participants in the technical webinar on the theme Quantum Computing, organized by the Electronics and Telecommunication Engineering Division of West Bengal State Center, IEI, through online platform. At the outset, I convey my sincere thanks to the panelists, Ms. Munmun Chakraborty, Joint Director, CDAC Kolkata, Mr. Sanjay Kumar Chaudhary, Joint Director, CDAC Kolkata. My sincere thanks also goes to Dr. Nirmal Das, Chairman, West Bengal State Center, IEI, Dr. H.O. Thackeray, President, IEI, Mr. Sandeep Kumar Dev, Vice President, IEI, Professor Dr. Girish Sri Krishnan Munda Dada, Chairman, Electronics and Telecommunication Engineering Division, Board, IEI, Dr. Ranganath G. Ranganath, Chairman, CATE, IEI, Mr. Chanchal Chakraborty, Vice President, Reliance Jio, and Convener, Electronics and Telecommunication Engineering Division, West Bengal State Center, IEI, and the moderator of this program. My vote of thanks also goes to all members of the Council and Division Board, members of Electronics and Telecommunication Division Board, all the members of the Committee of West Bengal State Center, IEI, and all the members of the ET Engineering Divisional Subcommittee, Director Technical, IEI, and his team for the wholehearted support to make the program success. Last but not the least, my sincere thanks goes to all who has given their silent support to make the program success. Thank you very much. And we are concluding the today's webinar here. Thank you very much.
Yeah, thanks.
Thank you all.
Thank you for giving us opportunity and good night.
And thank you, Dr. Chakraborty, for succinctly presenting what we have presented in so coherent and beautiful manner. We have presented a lot, and your presentation was better than us in a short span of time. It is really heartening that how much thing can be absorbed in a short amount of time and how it can be presented succinctly. So we are thankful for that.
No, sir, your presentation was so good, and we were engrossed in your both the presentations from you. So these become so much interesting. So we made, but we might have missed several points, but we tried to correlate and make in a coherence sort of these things.
Fantastic, fantastic.
Thank you, sir. Good night.
And the thing, whatever short noise you have discussed, this we are always used in our optical detectors, as well as our optical amplifiers everywhere nowadays. So we are aware of these facts, and you have described in a very beautiful manner. So this must be very much eye-opening to our listeners today, to our student community, engineering community, academia, everyone. Thanks one again to both of you, sir and madam, and thanks everyone present over here. Thanks our chairman and all the members present over here.
Thank you.
Thanks.
Thanks. Have a good night.
We shall be very happy to have you once again.
Okay.
But this beautiful discussion.
Great,
Absolutely,
great.
Ramda. We
It's a
want to
wonderful
make a
discussion.
successive
It's a learned
session.
discussion.
Yeah,
So
successive
we would love
session.
to have you once again.
Yes.
Yeah. I had a
And
talk
thank
with
you so
Munmun
much
also.
for your time.
Yes.
Thank you.
I had a talk with Munmun that we should make a series of presentations so that it will become, the quite comprehensive to all our listeners and to our academia as well as to our the students specifically, so that they can accept the challenge for this beautiful technology.
Thank you. Thank you. And
Okay.
good night to all.
Good night.
Good night. Good night, everyone.
Thank you. Thank you.
Thank you.
Thank you, sir.
Thank you.
Chanchal, you can close the session.
Yeah, I'll try.